Thank you all for being here. Um, so today we're going to talk about preliminary treatment and sedimentation. And this is just one session in our Tribal Wastewater Operator Certification webinar series. And so this is, I think, the fourth, maybe, one of these sessions. Um, and we're putting these on with the support from the EPA. Okay, and really quick, just who we are. You all probably know, but if this is your first time in one of these webinars, James and myself and Matt is here as well. We're from the Southwest Environmental Finance Center, and we're based at the University of New Mexico in the School of Engineering. And James and Matt are in Albuquerque, and I'm actually based in Billings, Montana. So I'm leading the work in EPA Region 8, so up here in Montana and surrounding states. And they're doing most of the work down there along with some of our other colleagues. And as part of this program, we have partners at Wichita State University Environmental Finance Center. And they're also in their program, they're also have the Heartland Environmental Justice Center. And they're, of course, in Wichita, Kansas. So, um, so they are also a great resource and doing a lot for this project too. Okay. And then really quick about myself. I'm with the Southwest Environmental Finance Center at UNM, but like I said, based in Billings. And I'm actually a certified drinking water operator, not a wastewater operator, but I've learned a lot about wastewater while working here. And I've been with the Southwest EFC for quite a few years now. So I've worked with a lot of you in person. And I'm going to be back in Albuquerque for the Rural Water Conference next month. So I'm really glad to get down there back to Albuquerque. And then we're going to be doing a training down there too. And then James, I'll pass it over to you. Maybe, um, oh yeah, you can introduce yourself and then we'll switch in just a second.
Okie doke. Yeah, I'm James Markham. Thanks for joining us. I've been in a few of these, and I'll be doing another one of these sessions a little bit later in August. I'm a research engineer here. I've been here for about a decade, and I work in the water and the wastewater side.
Awesome. Thank you, James. And then okay, and just really quick about this program. I won't really go over this too much, but this is a tribal wastewater program that we have as part of an EPA contract. And really the goal is to help you all just really meet your goals, whether that's helping you apply for funding for infrastructure. We're doing all kinds of trainings. We can help you with technical assistance, whether you need to troubleshoot some of your operations. Really whatever you all need is really what we're here for. And so please reach out. Our job is just to help you. And we have a website that you can go to learn more about our program. You can scan that QR code, or you can go to this website that we'll send to click on after when we send the slides out. Okay, and there's a few different parts of this. Like I said, we're doing needs assessments, so we can help you figure out what you can do to improve your operations, doing technical assistance and helping you get for funding, doing trainings, and then we're doing these peer-to-peer learning sessions, which we started starting out just in New Mexico. And I think we're having the second session at Sandia Pueblo in next week or a couple weeks or something. So please attend that if you're in New Mexico. Should be a great opportunity. Okay, and like I said, this is part of a series. Yeah, it looks like this is the fourth one out of 10. So please join us for our following sessions. Yeah, the next one we're going to talk about ponds and fixed film media, and then we're going to go from there. So all kinds of topics. Okay, yeah, and they're every 4 weeks, so roughly every month at the same time. Okay. Should we do this poll, James, or should we skip it? You have a preference? For the sake of time.
I think everybody has put their organizations pretty much into the chat, so I think we can skip it for this time.
Okay, perfect. Okay, so I'm going to stop sharing and I'll pass it over to you.
Okie doke. Let me make sure I've got the right screen showing. Looks good. All right, so we have a lot of content to get through today. I'll try not to go too fast, but if I do rush, please just pop into the chat to slow down, and Tucker will tell me to do so. There are a lot of words that start with P at the front end of wastewater treatment. And you need to really be able to differentiate between them, particularly for an OpCert exam. For the old hands here, most of this is going to be familiar, but if you're new to the wastewater world, it is good to get a handle on the vocabulary. You often hear about pre-treatment, which is things that happen to the wastewater before it even hits the collection system, let alone the wastewater treatment plant. We're talking about, fog traps at restaurants, fats, oils, and greases, and sometimes, industrial customers will screen and pre-treat their waste before it even gets into the collection system to move through to be treated. There's preliminary treatment, which is what we're going to be talking about today, which is largely about removing trash and large solids and grit. And then there's primary treatment, which we'll get to in a later session. But also will be covered a little bit under Tucker's session, which is the first step in settling out organic solids and floating off facts. So 3 things that start with P, really important that you remember which one, particularly in the context of OpCert questions, so that you know which area you need to be thinking about. All of these processes, of course, are really important and can't be overlooked. Typically when we're learning about wastewater treatment and the characterization of water, we're looking at things like biological oxygen demand and settlable solids, fecal coliform, other kinds of things, nitrates, phosphorus, fats, oils, and greases. And if you look at this table, which comes out of New Mexico's wastewater system OpCert guide, you see in the middle column there sort of typical concentrations of the wastewater stream as it's entering a wastewater treatment plant and what the goals are for the effluent that we're discharging. And you can see that we're looking for really huge reductions in pretty much all of these, anywhere from maybe a 50% reduction in phosphorus to possibly a 99% reduction of settlable solids. But what that table really doesn't cover is that there are a lot of other things that come along with the influent stream into a wastewater treatment plant that the biological processes cannot deal with. So stuff that can't be digested, and that other stuff is basically trash. It's non-digestible large organics like bones and sticks and roots, glass, sand and rocks, so those are inorganic, rags, building materials, toys, household items like the non-flushable, flushable wipes that everybody insists on putting into the trash. A lot of that other kind of debris shows up in the influent that hits your wastewater treatment plant. And getting that stuff out of the stream is just as important as the later stages, and in many cases, maybe even more important, because the efficiency of the later treatment stages can really be negatively impacted if your preliminary treatment steps that we're going to be talking about today either don't happen at all or don't work well, because this is largely about preparing the effluent for treatment. And I'm going to start off today showing you a really short animation that outlines the wastewater treatment process as a whole. This is from our website. For old hands, again, it's going to be a review, but for folks who are maybe new to the wastewater world, this will put our discussion today into context relative to the entire treatment process. It's a short video. It's only about 2 minutes. And I do want to note that if for some reason you want to put this on your own website, reach out to us. It's freely available. It's on our YouTube page. You can download it. It's a cute little video. So I'm going to play this, and this is actually a shortened version. The original is a little bit longer, but this kind of puts everything in context.
Let's take a look at how a typical wastewater treatment plant might operate. The first step in treating the wastewater is to remove any objects in the water that might damage the system. These facilities are known as the headworks. First, a bar screen is used to filter out large pieces of trash and debris that enter the sewage system. Some treatment plants also use grit chambers to remove sand, dirt, and other debris. This protects pumps and mechanical systems. Next is the primary treatment. The wastewater is added to a settling tank, or clarifier, which the water sits for several hours, allowing the heavier solids to settle to the bottom and scum consisting of fats and oil to float to the top. Both the sludge and scum are removed, which significantly reduces levels of harmful substances from the water. The water then continues to secondary treatment. Secondary treatment uses bacteria to digest the remaining pollutants. In aerobic treatment, the wastewater is forcefully mixed with bacteria and oxygen. The oxygen helps the bacteria to digest pollutants. The water is then taken to a settling tank, where the sludge again settles and is removed. Next begins chlorination and chemical treatment. Wastewater contains many human-centric organisms that are associated with various waterborne diseases. Chlorine is added to the water to selectively destruct any disease-causing organisms in the water. Some treatment plants add an additional chemical to the water to remove any remaining chlorine prior to discharge. This dechlorination protects fish and other aquatic life. After treatment is complete, the water is discharged back into the environment, either into surface water or into the ground, while solids are dried and disposed of or used for fertilizer. Effectively collecting and treating wastewater is important to the health of every community, including the people and the environment.
All right, so that's a very basic overview and something of an oversimplification, but it covers pretty much all of the basic steps in wastewater treatment and shows that the steps that we're going to be talking about, the preliminary treatment, happen at the front end of the treatment process at the headworks, which is sort of the name for those processes that happen at the front end. So we're talking about screening large items, taking big pieces of trash out from the wastewater, which is typically followed by a grit removal stage, which is designed to remove sand and gravel. There's a couple of different ways this can be done, and we'll talk about the specifics and show you some examples of equipment that does this. But the discussion is, in a way, kind of a continuation of our last session because we were talking about mechanical systems and devices. And we use a lot of different mechanical systems in these processes. And as we've stated in prior sessions, even though your wastewater treatment plant might not have all of the things that we talk about, and again, many of the pieces of equipment that we're going to discuss today are kind of variations on a theme, typically you're going to be responsible for knowing more or less how they work and their function on an OpCert exam. So it is good, even if you're not working with these on a day-to-day basis, to have an understanding of what functions they perform. It's also good to realize that even though most systems have some variation on the theme that we're talking about today, the complexity is really going to depend on the size of your system, when it was built, and what kind of treatment you're doing. Albuquerque's preliminary treatment facilities are quite complex. There's a big building that houses a lot of different kinds of equipment. Other systems, like the one that we'll see a video of in a little bit down in Gatesville, is much smaller and a little bit simpler. It's got a bar screen, some sieving action, a grinder, mechanical belt. But again, even though the complexity of these systems are widely different, they perform essentially the same function. And they often incorporate multiple stages. So, for example, that screen system that I just showed you down in Gatesville is followed by a drum mechanism that captures even smaller particles. And sometimes the systems are very, very basic. A basic lagoon system might start out at the headworks having something similar to this. This is just a basic bar screen to capture large trash, followed by some grit channels that allow grit and other heavy solids to settle out. Again, which version of this you have is going to depend largely on the complexity of the treatment process that you need to do, the size and the flow, and when your system was built as well, because different kinds of treatment come in and out of vogue. But all of these processes have one thing in common. What is that? Well, one, they're preliminary. They happen at the beginning. So they're coming before primary treatment. And the second one is that they're all physical processes, right? They're processes that are focused on moving large inorganic material out to facilitate the later biological treatment, as that video pointed out. It's about removing that debris. All of the kinds of debris that you are trying to remove in preliminary treatment can damage pumps, they can clog pipes, they can take up space in your process tanks further down the line and really negatively affect their ability to do their job correctly. And that sort of sentence that I just gave you there kind of gives us the real reason that we have preliminary treatment processes in place. They protect the equipment that's further down the line. They protect the pump, they protect the valves that could get jammed or broken or get made less efficient if larger materials were allowed to pass through to them. And then in turn, of course, that protects the environment because clogged pumps, filled up channels can lead to inadequate treatment or in some cases overflows. So, preliminary treatment helps you comply with your permit requirements as well, even though there typically aren't biological processes going on there. Essentially, what you're doing is you're prepping the wastewater for the real primary and secondary treatment. And as we'll see, again, most of the processes that we're going to talk about are entirely physical. You can really think of preliminary treatment as a series of sieves. Sieves or strainers are a really good analogy. We are taking out solid materials of varying sizes in varying stages. A tea strainer is a really good analogy, right? You make the tea, you've got loose leaves. You need the leaves to make the tea, but you don't want them in your cup. So you strain them out, but of course, not implying that you want to make tea out of wastewater, but with a cup of tea, the first preparation is that straining out of the leaves, and that's sort of the same analogous process that's going on in wastewater treatment. So to summarize, the short version, preliminary treatment is just about the removal of things like metal, rock, sand, eggshells, and other materials that can hinder plant operation. And how do we do it? We use equipment like bar racks and screens and shredders and grit removal systems, all of which we will sort of show you in more detail in a second to do that. So that gets us to our first poll question, which is, what is the main purpose of preliminary treatment? All right, yeah, so the correct answers in this case are the first answer, protecting the equipment from damage, and the last answer, which is essentially preparing the influent for primary treatment. Biological treatment typically does not happen during the preliminary stages, although there is one exception we will get to at the end of my presentation here. And the making inorganic material more digestible is a bit of a red herring. Bacteria digest organic material. So it's the first one and the fourth one. All right, so let's actually get into some of the kinds of equipment that you're going to see. Preliminary treatment facilities typically start with coarse screening of some kind. Typically, these are going to be bar screens or bar racks. I've got a couple of different versions shown here on the screen. The one on the left is a manual screen, and you can see the flow goes through the bar racks. You basically just got a bunch of slanted racks that trash can pile up on. There's a trough or a pipe at the top where that trash can be periodically raked into and dewatered. And then on the side, you'll typically have some sort of a bypass pipe so that just in case things get backed up or if some maintenance needs to be done, there is a way for the effluent to flow around that. The version on the right is basically the same kind of operating principle, except it's got a mechanical cleaner on it. In this case, there's a rake on the front that is periodically cleaning the trash off. The purpose, again, of these sort of initial stage bar screens or trash screens is trapping larger debris. This is what they often look like, the bottles, the styrofoam, the plastic bags, the things like that. They're just sets of parallel bars that are mounted in a channel, slanted so that the wastewater can flow through them with the purpose of trapping large trash and rags. Because they're completely submerged all the time, they're typically made out of non-corrosive metals, so they're either going to be aluminum or stainless steel. And they're referred to a little bit differently in different parts of the country, but typically the way they're referred to is based on the size of the gaps between the bars. So if it's a really larger gap, so 2 inches or higher, they're typically called trash racks or bar racks. Anything below 3/8 and 2 inches is typically called a bar screen. You are not going to really have bar screens with gaps smaller than 3/8 of an inch because they would plug up too quickly and potentially cause overflows. Typically, bar screens have a couple of channels so that you can balance the flow, but not always. And sometimes you'll want to be able to sort of take one channel out of operation while the other one is while the other one is still functioning so that you can clean them. Thing that is really important to remember is that bar screens have to be cleaned periodically, typically at least daily, quite often more often than that, hence the mechanical options. The size of the screens and racks really depends on the size of the channel that they're in. So a small setup could only be a couple of feet across, whereas a very large installation could have multiple bar racks or bar screens that are 10 feet or more across. And it's really important to clean those because, like anything that you put in a channel, bar screens cause head loss because they restrict the flow. So if you look sort of sideways, and I'll show you a picture here in a second, the flow below the bar screen is typically going to be lower level than the flow above it because of that head loss that the bar screens induce. And the more trash that builds up on it, the more head loss you have, and the more the influent velocity upstream of the bar rack decreases. And you really want to be maintaining specific velocities at different parts of the treatment process for reasons that we will get to in a minute. So could be really basic, could be something like this, could be a manually cleaned rack. You can sort of see the parts there. You've got the flow at the bottom, you've got the slanted racks in the middle, you've got the people standing up on the gantry above, and you can see that channel in the top of the rack where the trash gets put initially when it's pulled off the racks, because dewatering is really important. You basically have to allow the liquids to come off, and those get channeled back into the influent stream. Cleaning, like I said, it's important. You don't want excessive trash buildup. You could also have a mechanically cleaned option. Here's a little short video. There's no sound, but it kind of shows you how this works in the background, where you will have a mechanical cleaning system on the rack, where the cleaning mechanism is triggered either by a timer or by a differential pressure switch that recognizes the pressure differential caused by the head loss, and triggers that cleaning mechanism. Some are actually continuously run. The point is, the bar screen is there to trap trash, and rakes, whether mechanical or manual, come down, clean the trash off. There are a lot of different versions of these, and sort of the big divider is that some have the teeth in the front of the bars, sort of upstream, and some have them downstream. And each setup really has its pros and cons. If those cleaning teeth are in the back, they jam less, but they don't clean quite as well. Whereas the cleaning versions that are in the front remove more trash, but they're more liable to jam. You might actually even have mechanical and manually clean screens at different stages, because like that picture of the sieves I showed you, quite often you have a succession of essentially finer and finer sieves taking out those solids. But again, they need attention, particularly the mechanical versions. They have to be inspected quite often. They have to be lubricated quite often. They have to be tested. This is one of those areas where it's really important to read your manuals and follow the SOPs. I'm not going to talk about the specifics of SOPs because it's going to vary for each kind of equipment that you have. But if your system doesn't have SOPs or standard operating procedures related to mechanical equipment, it's really important to develop some. We'll talk about those a little bit in later sessions, and you should also really have, daily inspections as well as, weekly, monthly, quarterly, and annual maintenance routines to take care of this equipment, because it really is your front line of defense. And breakdowns here can have, large negative effects on the treatment further down the line. And speaking of repairs, I just do want to mention we are going to have an entire session on safety, but these mechanical systems have big motors, moving parts. They can easily injure people. So if you are going to be working on these, again, it's really important to know exactly what you're doing, to use the PPE that you have, to understand lockout and checkout procedures. And if you don't know what I'm talking about, you should not be working on electrical equipment. Basically, you want specific procedures in place to make sure that any equipment that is being worked on is powered off and doesn't accidentally get switched on while somebody's working on it. People get hurt and killed every year in all kinds of industries because those procedures, those lockout procedures, are not followed correctly. But regardless of how they're cleaned, the racks need to be hosed down frequently to prevent slime buildup, and they need to be cleaned frequently to prevent blockages and stop the buildup of detritus that can cause odors and attract flies. Now, of course, you got to do something with the stuff you take off the rack. The term for the debris that comes off of the rack is screenings. And there's a couple things to remember about screenings. It is trash, but you can't just pull it out and toss it away because it's wet. In most cases, you're not allowed to deliver screenings that still have liquid on them to landfills. So you've got to make sure you have a way of draining the screenings, draining them back into the influent. So here you can see that channel they've got at the end of theirs, and the screenings basically sit there and dry off essentially before they are completely disposed of. They have to be dewatered and they have to be disposed of on a regular basis. Again, they are typically going to have some organic material on them. And the last thing you want to do is sort of have proliferating disease-causing organisms or vermin attracted because you're not handling your screenings in a good way. In other words, you're letting them sit. And you can see in this picture off to the right-hand side, there's some trash on the ground. That's the kind of thing you want to avoid. You don't store the stuff on the ground. You want to make sure that it's treated correctly, that it's dewatered, and that it is disposed of on a regular basis so it doesn't, again, attract vermin or cause odors. This is one of the things that the folks that live around wastewater treatment plants complain about most is the smell, and one of the best ways to help avoid odors is to deal with the trash appropriately. This slide is in here just so you can sort of read it later and recognize that there are different sizes of screens, and the way they're classified is basically based on the size. And you could have a system that literally has all three of these, where it starts with maybe a manually cleaned bar screen that has very wide gaps, a couple of inches. Mechanically cleaned bar screens are typically going to be handling equipment, screenings that are sort of between the 0.3 and about a ½ inch in size. And there are fine bar screens, which are almost always mechanically cleaned, that might be handling trash down to like 0.1 inches. So relatively small. Which brings us to our next question. So we talked about bar screens, we talked about bar racks and trash racks. What are bar racks or trash racks going to remove? The biggest pieces in the influent stream or the smallest? All right, so yeah, pretty much everybody got that right. Bar racks are going to be handling the largest. Bar screens tend to go after the smaller things. One way to keep this in your mind might be to think of your screen door on your door on a house versus the security door that has bars on it, right? The screen doors have smaller openings, they keep out smaller things. So bar racks and trash racks are focused on large trash, whereas bar screens are focused on smaller, but not the smallest trash. Let's talk a little bit about solids reduction. There's a couple of different ways that you can deal with trash in the effluent stream. One is to capture it. Another step before maybe capturing it later is to make it smaller. Again, this is all about protecting equipment, and one way to protect equipment from jamming is to chop up the stuff that's in there so that it's smaller and it can pass through your equipment without damaging it. There's sort of three basic types of equipment that we use for this: macerators, grinders, and communitors. All of these are basically giant garbage disposals. You can sort of think of these as like a big version or industrial version of the garbage disposal in your sink. It doesn't get rid of what goes in, it just chops it up into really small pieces that can pass through the pipes and further down the drain and into the wastewater stream. Now, of course, you have to get it out at some point, but one way of protecting equipment is to make those bits smaller. So communitors, it's kind of an older style that basically is just a giant shredder. It's typically focused on things like rags and debris that are left in water. One of the downsides of these is that they're still leaving bits and pieces in there, which can clog equipment, which can be labor intensive to rectify. And these are typically using very powerful motors, unlike sort of a manual bar that basically only uses human power to run them. So you're going to need a lot of electricity, and you can sort of see the cross section of the way these are built. The influent stream comes out of the bottom, so when they do jam up, they are a little bit of a pain to clean. They can take place the place of the bar screens. The downside is that they still leave that stuff in there, and this is a video of one of those in the works. Now, this isn't the best setup. There are no safety guardrails around this, and you would not want to fall in there and get stuck in it. But it's basically a giant garbage disposal that grinds up anything that goes in there. So again, pros, having these can sort of eliminate the need for a bar rack or a bar screen. The con is that you still have that shredded material in the wastewater stream, and you have to take it out further down, and they require power. Grinders are something that show up in a lot of different places in wastewater systems. So they're often at the headworks, but you might actually have versions of these in your your collection system as well, or these might be used in combination with bar racks. So these typically come in a variety of sizes. This is not an endorsement of these particular grinders. It's just kind of a nice image of different versions that they have available. These often show up in lift stations, so to help make sure that pumps out in the collection system don't get clogged. They may be in headworks as well. The thing about these is they can typically run dry. So here's an example of one near a lift station, and you can see half of this is sticking out the water. It's not pressurized. This is the upstream side. You can see it's got sort of a rack that catches trash in it, and then it's got those spinning blades. The downstream side looks like this, and it basically chops everything up and squishes it through those little gaps. They'll often also have bypass screens or bypass racks to provide trash removal in the event that the grinder itself needs some maintenance, and they typically will need periodic maintenance to maintain them functioning correctly. And then there are macerators, which are the same principle, typically designed for chopping up smaller bits. Those big grinders, they'll chop up a boot and the foot inside it if you're not careful. These macerators are typically in line, in a pipe, pressurized. If you look closely at these, you can see it's kind of like an upside down sausage maker, right? You got effluent coming in and from the left, going through those blades, which are sort of spinning around on that grate. They're self-sharpening. You've got a bucket at the bottom or a space at the bottom trap where larger materials will fall so that the machine doesn't get jammed up. And what comes out the other side is finely cut small bits. This are typically things dealing with things like wet wipes, plastics, hair, small stuff that can be chopped up, and it's typically in the sort of medium coarse to fine cutting. The difference between these and some of the other equipment is they do not run dry. The solids have to be completely suspended in a liquid stream. Again, like with these other types of mechanical systems, all they're doing is making the trash smaller. You still have to get it out of the wastewater stream, which brings us to fine screens. There are a lot of different ways to get the small bits out. These is not an exhaustive list, but I'm going to show you some pictures of some sort of typical fine screens that are used in current wastewater treatment. There are step types. This is essentially, it looks kind of like an escalator. So influent is coming in at the bottom left here, and this belt has teeth on it, and it's just rotating constantly and picking up anything solid that's in there. And you can see from the picture, it's picking up toilet paper, small bits of food, beans, bottle caps, little stuff. And the gaps between those wires are quite small. So these are very effective at screening out materials. Another kind that you'll often see, and we saw a picture of this earlier from Gatesville, is this perforated plate version. So this is a continuously running belt. you can see that about every 5 plates, there's a plate with teeth on it. Those plates have holes in them. There's a bar rack at the bottom of that well. That's sort of the first stage. The effluent goes to this, and as it passes through this perforated plate, the liquid stream continues underneath, and this plate basically just grabs whatever's there and lifts it up to the top, and where it can be disposed of. This is the top end of that same system, and you can see as it comes up here, there's a dewatering process. That's what this essentially is. The liquid's dripping off, and then it gets pumped over into this hopper where it's disposed of regularly. So up close, those perforated plates look something like this. They come with a variety of different hole sizes, but you can see basically the solids stay on one side, the liquid drips through. So it has the advantage of essentially dewatering the trash as part of its job. Anything that's bigger than the perforation gets taken out of the stream. Anything smaller, which is typically going to include grit and organic suspended solids, which we haven't talked about yet, will stay in the stream. Another option is something called a wedge wire, where you've essentially got a static bunch of wires with very, very small gaps in between them. And you've got these combs that go through the water and push up and through, and everything that they bring up and it's solid gets caught and dealt with at the top. This happens to be a system at a small plant in Tenino, Washington. It's a little hard to see, but the gaps in there are about 2-millimeter openings. They have 2 of these that are designed to handle about 250,000 gallons a day. And this is something really important to think about. These are stages on a continuum of getting out, larger trash to medium-sized trash to smaller trash. And you have to make sure, particularly if you are retrofitting a system, that you consider the size of the particles you're trying to get out. The operator of this particular system mentioned that because they have grinder pumps at each house that chop the bits, the trash down into very, very small bits, many of the screenings are actually too fine for this particular screening method to be effective. So they're having to look at a different way of getting out those smaller particles. And that's basically because their upstream processes chop the trash that becomes the screenings into too fine a material to get through. It's kind of like with your coffee filter. If you've got an old coffee filter, or quite often like a really, really fine grind, some of those coffee grinds will end up in your cup because the filter that you have basically just can't handle them. So something to think about. Another sort of option for this is a static screen. One of the advantages of this kind of setup is that there are very few moving parts. So the way this works, if you look at the image on the right, which is sort of a reverse image of what you're seeing on the left, water comes in through the top, goes into a trough, is dumped out onto the top of that parabolic screen. And as it slides down, that screen has holes in it, kind of works like the perforated plates. Water drips through, and the solids that are larger than the holes scooch their way down that rack into that trough. It's at the bottom. And if you look at the left-hand picture, you can see there's some sprayers there to sort of help facilitate that. And then there's a worm screw at the bottom that takes all of the detritus that comes off of that screen and moves it on for further processing. One of the advantages of this type of system is it basically has no moving parts other than the pumps and the worm screw at the bottom. They're relatively low to install. They don't require a ton of maintenance because they have sprayers built into them, basically just need regular cleaning. And they operate pretty quietly, and they're pretty effective because you can get different size screens for these. Another option that you might run into is the rotary drum. At the Gatesville plant that I showed you, they've got bar screen, they've got that perforated plate system, and then for the really small stuff, they have a rotary drum mechanism. And the way this works is that influent comes in through the center, there are spray bars, that drum is constantly turning, the liquid flows through the drum is perforated, and the solids get trapped on the inside and get discharged out the back. So all variations on a theme, they're all just different kinds of sieves. things to remember when you're talking about screening and grinding, because we've talked about both. Comminution or grinding just reduces the size of the larger materials in the influent stream. And that is good because it helps it move through equipment without jamming up pumps, but you still have to get rid of it. The screening processes actually remove material from the influent stream, and how well they do that depends on the size of the screens. And again, you may have multiple stages focused on different size materials. Screening and comminution essentially grinding and comminution essentially prepare those larger materials for further treatment and removal by reducing their size. Screening is what ultimately protects that downstream equipment from damage. I'm not going to go over the details that are listed on here, but there are different kinds of racks and screens, and the size of material that you can take out of using them is listed on the right-hand side. This slide will be included in the PDF that we send you, so you can take a look at it when you get that. Obviously, we've been talking about taking trash out in a variety of different ways. Ultimately, you have to dispose of that. And the screening process can actually generate quite a lot of material. So you're going to get anywhere from probably 1.5 to 8 cubic feet of screenings for every 1,000,000 gallons of water that you treat, depending on the screen size. Obviously, the smaller the openings, the more stuff you're going to catch. Those screenings have to be dewatered. They have to be disposed of. And because, again, they have typically some organic matter still included in them, might be disease-causing organisms, that stuff's going to attract vermin. So, excuse me, you have to manage the buildup of screenings at your plant so that they don't become a nuisance, because they're hazardous to everybody. They're hazardous to operators. This isn't stuff you want laying around. So it's something you have to manage. Small plants might not collect a lot per day, but you don't want this stuff to build up. So you want to store it securely. They're typically going to either be sent to a landfill and buried, or they're going to be incinerated, depending on what part of the country you're on. There are very strict environmental regulations and permit requirements that govern these processes. And this is one of those things that we're not going to go into detail right now. This is one of those sort of check your local listing situation, understand what the rules are in your particular jurisdiction, because they vary quite a bit. So that covers all of the big trash. What else is left after that? Well, sand and grit. So let's talk a little bit about the grit removal process. First off, what is grit? It's typically defined as particles that are somewhat bigger than 0.2 millimeters, so 8/1000 of an inch, typically mostly organic. So this is sand, cinders, rocks, coffee grounds, eggs, seeds, stuff that's mostly inorganic. It's not digestible. So the biological treatment processes you have in your plant aren't going to have any effect on it. So you need to get it out of the system. There is some modern equipment that will move grit down to 0.006 of an inch. We're going to talk about some of the different ways that we can do grit removal. There are some very inexpensive low-tech ways, and there are some more expensive, very high-tech ways. The simplest way to do this, because what we're trying to do here, again, is get the inorganic suspended solids out and keep the organic suspended solids in suspension so that the primary and secondary treatment stages can deal with those. So we're trying to get out that inorganic grit, but keep the other stuff in. And how do we do that? Well, one way is to control the velocity of the wastewater as it's flowing through the system, because at a velocity of about 1 foot per second, the grit will drop out of the water and fall to the bottom of the channel, but the organic suspended solids will not. Which leads us to our first sort of basic kind of grit removal process or operation, which is using a grit channel, like the one you can see in this picture here. This one happens to be in Kenya, and there are some issues with it. The biggest one being that there's a large pile of unattended grit sitting over here on the side. But it demonstrates pretty clearly how these things work. You've got water coming through the bar screens at the front and flowing through these two channels that can be operated singly or together. And those are designed to slow the water down to about 1 foot per second so that sand and grit and eggshells will fall out to the bottom, and then they periodically get cleaned out. So that piece right there is the grit channel. This is a very small, simple one. They can be really, really big as well. For every million gallons of water, you're in addition to the up to maybe 8 cubic feet of screenings, you're going to have somewhere between 1 and 4 cubic feet of grit, maybe more, maybe less, kind of depending on where you're at, what ends up in your system. So grit channels are kind of the low-tech way of doing it. They're all more or less designed the same way. You've got typically 2 channels with slide gates so that you can control the flow. There's a settling area, and as Tucker will show you in the sedimentation, he'll show you the physical processes that go on there. But then you've got, at sort of the end, you've got weirs that you can use to control the speed of the flow, and then the grit periodically gets taken out. Again, got a slide in here with some vocab for you that you can study on your own, but pretty much all grit channels will have these components, and you will be expected to know what they are and what they do. So, you know, that a weir controls channel velocity, that you typically have a drain valve so that you can drain the channel for inspection or work on it. You will often also be required to understand detention times. A typical grit channel has fluid staying in it for around a minute. It can range from about 45 seconds to a minute and a half. And again, you're looking for that sweet spot velocity of about a foot per second. Could be as low as 0.8, as high as 1.3. And the velocity of that stream will determine how much falls out of what size. So that's the very basic version, where it's just, you know, a channel where you're slowing things down. There are also more high-tech aerated grit chambers. So you're looking sort of a top-down section on the left and a cross-section on the right. These are very typical for newly designed plants. They have very high removal rates. They can remove 95% of the grit, and they use air in the grit chamber to both move the water around, but also to make the water less dense so that the grit falls out easier. One of the main differences between an aerated grit chamber and sort of the old school version is that the detention time is typically much longer in an aerated grit chamber. It could be as high as 5 minutes, typically not less than 2. These are also fairly large. They'll get out typically about 2 cubic feet of grit per million gallons of treated wastewater. They have several other advantages too, one of which is that you are pumping air into this. So as I said in the beginning, most of these are entirely physical processes, but you sometimes do actually get a little bit of biological treatment in an aerated grit chamber because you're pumping oxygen into that. The aeration process also helps to essentially freshen the influent by removing some odor and hydrogen sulfide gas that might build up. And it can help prevent the wastewater from going septic. So even though I said, you know, most preliminary treatment is physical, this is sort of the one exception, or one of the 2 exceptions, where you might get some low-level organic content removal in this kind of a tank. They also allow for chemical additions should you need that. Basically, the way they work, you've got the sort of cross section, you've got bubblers on one side that create a current, causes the water to sort of flow around in this barrel format as it goes down the channel. The air-water mixture has a lower specific gravity than water, so that basically just causes the grit to fall out faster. And then that rolling action also helps to move the grit as it's falling down into that channel. And there's scrapers typically at the bottom that will collect the grit and move it out. So, you know, the grit basically falls to the bottom and gets pulled out. Other options, you might have a cyclone separator. If you've ever worked in a wood shop, you might recognize this. A lot of dust collection systems are set up like this, where you've essentially got your influent coming in at a tangent to a barrel. It spins around, and the overflow of liquid goes out the top, but the vortex that's created, the cyclone that's created on the inside, basically spins all the particulate matter out to the side where it settles down to the bottom. In a wood shop, they're typically straight up and down. In wastewater treatment, they're typically on their sides because they'll be combined with some sort of screw or auger mechanism so that the grit that is settling out the bottom has a chance to be dewatered as it's moved into a storage bin and moved to a place where it can be taken off site. These do great job. Downside is they require energy. You have to have pumps to make them work. And of course, you've got to have coarse screens in front of these units to make sure that they don't get clogged up. You might have a vortex separator, which is works on a similar principle, but these are typically proprietary. There's specific companies that make them, but basically the idea is the water comes in at a tangent, spins around, and as it's spinning around, the heavier grit falls to the bottom where there's a grit pump that pumps it out, and the cleaned fluid goes out the top. These are typically used where there's a lot of very fine grit. They can remove up to about 75% of grit down to 4,000ths of an inch, which is very, very small. They've also got generally very consistent removal flow efficiencies over wide ranges of flow. And aside from the pump at the bottom, they don't have any moving parts. They also typically have very low head loss and a small footprint, much smaller than a settling basin. So as plants are being designed, obviously space is a concern. So you might have a vortex system set up because there just isn't room for an aerated grit chamber, which tend to be very, very large. The downside of these, of course, is that they can get clogs in the grit sumps, which are down at the bottom, so it makes them a little hard to clean and work on. And they're typically proprietary. Like I said, there's some companies that make these, and you'll have to get maintenance and spare parts and things like that directly from them. And ideally, like you would want to have 2 grit channels, you want to have redundancy with these as well so that you can deal with repairs or unexpected high flows at a small plant. But typically small plants aren't going to be able to afford these because they're quite expensive. Once you got the grit out, again, you've got to dispose of it. And like the other trash that we pull out, our screenings, it tends to be wet. It tends to have organic material on it. One way of dealing with this is through grit washing and classifiers that dispose of it. And we're sort of looking at a cross section of one of these here. And you can see that, there's an inlet at the top. The grit goes in. It's essentially washed and agitated in this bin, and now cleaner grit settles to the bottom, gets moved out with a screw or a belt. The liquid that's in there drains out and goes back into the effluent stream. Here's a short video of one of these things in action to kind of give you the idea. Basically, you're just pumping the grit into what's essentially a large washing machine and sucking it out of the bottom. So that the grit that you are getting rid of is a little bit cleaner, is less likely to attract vermin, have bad smells, things like that. So, and again, not an endorsement of the company, just a really good video, one of the best ones I could find. Of course, the grit screenings end up in a hopper somewhere at the end. And that equipment itself can be very, very complicated. So the picture you're looking at right now is Downers Grove, Illinois, which is a relatively good sized town. And they have a variety of locations in their plant that deal with grit. And they've got this belt conveyor system that moves it through the plant and out of the facility, which in and of itself is quite complex. This is another much smaller option at Picnic Point in Washington State. This particular hopper is getting screenings and grit from their wastewater treatment plant. So the far left is screenings. There's nothing coming out at the moment, and you can see the smaller pipes at the middle, and on the right, those are grit disposal pipes. All of that ends up in the same place, and it gets taken out to the wastewater treatment, out to the landfill. Grit's typically also going to go to a landfill. Ideally, you want to get rid of grit daily so that it doesn't build up. You want to be looking for organic matter. The quality of the grit can tell you a lot about your processes. If there's a lot of organic matter in there, then the flow rate and the velocity is too low, because if the liquid is moving too slowly, organics will settle out too. If you're seeing mostly big pieces and heavy sand, check the velocity. It might be going too fast. So this is one of those things where, you know, you don't want it to be too slow. You don't want to be too fast. You want it to be just right. And analyzing the grit that comes out of your system can give you a good idea of whether your systems are dialed in. Last thing I want to talk about real quickly is flow measurement. This is typically going to be the last stage in preliminary treatment. You got to know how much liquid is going through or effluent is going through your plant, right? You're typically going to use meters or some kind of weir to do that. But every plant has permit requirements if you're not in terms of the amount of daily flow, and your processes are largely determined by flow. So you got to measure it. If you don't measure it, it's going to be really hard to run anything but the most simple system efficiently. There's a lot of different ways that can be done. Mag meters, like you see in this picture. You might use, you know, a weir or a partial flume like these. The point is, there's going to be some kind of flow measurement, typically at your wastewater treatment plant. Keeping track of flows is typically part of your permit requirements. So you want to make sure that this equipment works and that you understand how to read it. And keep those records daily, because again, quite frankly, quite often you may run into situations where there's a pulse that goes through, something happens with your treatment where it's not treating as well as you want it to. And one of the main tools you're going to use to investigate your processes is understanding the flow. Last but not least, part of this process might include some flow equalization or specific pre-aeration processes. We've talked about before, most wastewater treatment plants don't have, or most wastewater treatment systems don't have a consistent flow all the time. People get up in the morning, they take showers, they cook. That large pulse moves through the system, typically hits the plant somewhere around 10 or noon, and then things taper off. So one of the ways that you can effectively deal with these changes in flow is to have basins that you can use to hold flow and regulate it, so that you've got a consistent process in your wastewater treatment plant and you're not being sort of subjected to these rising and lowering tides, if you will, of flow that's coming through the collection system. When you have these, aeration is a must, because otherwise that stored influent can go septic prior to treatment. And again, create offensive odors and things like that. So this is the only other portion of preliminary treatment where you might get some biological activity going on, depending on how it's set up, because essentially you're pumping air into this system. So again, two things to remember. You know, flow equalization is essentially just having holding tanks so that you can make sure what's going through the treatment processes is relatively consistent. Use that to essentially, again, even out the flow. Might actually allow you to have a smaller treatment plant. That being said, it's not all that common here. It's something that is more often used in Europe, and I think it's because they tend to have less space to put their treatment plants. And even so, even if you have flow equalization, you really have to be able to account for extreme flows. And again, the pre-aeration is there to add oxygen and reduce smelly gases. Hydrogen sulfide stinks like rotten eggs. Methane doesn't have a smell, but it can be problematic. You know, this is all about odor control. There are a lot of complicated ways to do odor control that we're not going to kind of go into today, but there are a lot of different kinds of gases that are produced as part of natural decomposition. Hydrogen sulfide, ammonia, ethane, indole, scatol. None of these smell very good. And if your plant is not well run, they can build up. There's a lot of other natural gases that, you know, can be processed as well. Complex plants will have a capture and treat method. You know, that Albuquerque building I showed you, it's capped. They have a huge ventilation system. Most smaller systems aren't going to have anything this complex. The simplest way to deal with odor control is to essentially be on top of your screenings and your grit removal, removing them frequently, making sure that you maintain good housekeeping so that things don't build up. Make sure that those screenings are dewatered and removed frequently. Again, if they sit around, the piles go anaerobic, they start to smell. The best way to avoid that is to, again, clean house on the regular. With that, we'll do our last poll question. I realize we run a couple of minutes behind here, but we talked about a couple of different stages. This poll question is all about what order 3 of those might be in. So we've got grit removal, we've got screening, and we've got flow measurement. What order from first to last would those typically be in? Right, yeah, most of you got that right. So you'd start with screening, then grit removal. Flow measurement typically happens at the end. So screening, that's your bar racks and your bar screens, looking at the big stuff. Grit tends to be smaller. That's your sand, that's your rocks, your eggshells, your coffee grounds, which would be sort of in the next smaller sieve. And then obviously you want to measure the flow before we go through. All right, so that's the end of this section. Why don't we take a 5-minute break so everybody can hit the restroom and get some coffee, and then we'll come back and we will talk about sedimentation.
Now we're going to start the second part of the training today, and this really is kind of just a continuation of what James was talking about. So we're kind of just going through the whole treatment process. And so after what James talked about, then really the big next step is sedimentation. So in this first slide, this title slide, I got this picture from James, but I thought it's a really nice picture because we're used to staring at wastewater all day with this training, and we just are looking at that. So might as well have something analogous. So this is snow falling, and of course the snow is falling, it clumps together, and it falls down because the snow is heavier than gravity, or sorry, more dense because of gravity, because the snow is more dense than air, which is it is falling through. So. Okay, so before we talk about sedimentation too much, we're going to talk about the specific terms that are important for that. So these include specific gravity, sedimentation, coagulation, flocculation, and flotation. Okay, so the first one I wanted to talk about is specific gravity. So you'll see on the right, there's this device here. Put in the chat if you know what this is called or if you've ever used one. And if you have used one, let us know what you used it for. So how this device works is it is a graduated cylinder, and you put whatever your sample is in here. Then you mix it up with this little metal rod thing. Then you put this little bulb in there. And so depending on the density of now like the liquid, the mixture that's in the cylinder, that bulb is going to float higher and lower depending on how thick that is, or really what the density is. And this is one way to measure specific gravity. And specific gravity, it really is just a measurement of the ratio of the density of one substance compared to water. And so there's an equation for it. So specific density is the density of that substance divided by the density of water. And so water would then have a specific gravity of 1. And so because this is a ratio of 2 different densities, the units cancel out. So this is a unitless measurement. So there's no units on this. It's just a value. Okay. And then, so for a specific gravity of less than 1, that means that whatever's suspended in it is less dense than water, and a specific gravity of 1 is more dense than water. And I don't know if I can see the chat here. Yeah, hydrometer, thanks. All right, Kenneth, you get a, I don't know, virtual high five. So yes, that's called a hydrometer. And in this specific example, this was something I was actually doing this, and I was measuring soil. This was a soil sample, and it's used to measure the amount of soil or sand, silt, and clay. So how big those particles are. So just like James was talking about with grit, you can only measure any kind of soil, or people also use this to measure the amount of alcohol in beer, I think. So there's all kinds of things that you can use that you can measure with this device. And it's interesting too because you mix this up and then you can put it in. But if you wait a certain amount of time, the things will start settling out. So then the density of that liquid will change. And so you can measure how quickly things are falling out of suspension. So pretty simple, but pretty cool device. Okay, and then the next term is sedimentation. So this really is just the settling of denser particles in the wastewater. And so this is, of course, what the whole thing we're talking about here is. And this really is this is accomplished by slowing down the wastewater stream. So the slower water moves, it no longer has that energy to keep things suspended. And so once it slows down, things settle out. And then the next one is flocculation. So this is a term that refers to the physical gathering of different particles. So this is a physical process. So as wastewater is moving, it's going to be bumping into each other. And this can be artificially created through a mixer or something. But the whole concept of flocculation is that all these particles are bumping into each other. And as they're doing that, they clump together and create bigger and bigger chunks. And so the bigger those chunks are, they fall down quicker, because just like how if you're going swimming in a swimming pool, you may be more dense than water, but you're not going to fall that quickly because water is viscous. And so but if you have a bigger and bigger mass, you might fall down, you drop out quicker. So that's the idea of flocculation. Bigger particles going to drop out quicker. Okay, and coagulation, you'll notice that this term was actually in that definition of flocculation. So whereas flocculation is the physical clumping of particles, coagulation is the chemical clumping together of particles. So in wastewater, as well as in drinking water, most of the stuff coming in has a negative charge to it. And so it normally doesn't want to, it usually separates, it doesn't want to clump onto each other. And so coagulation, oftentimes a chemical is added, usually later in the process, not for the primary clarification, but that will get rid of these negative charges, and then the particles will clump together and also make bigger clumps that will settle out quicker. So that's the science behind that. And you'll regularly hear flocculation, coagulation in combination to each other, and so just know that. And then lastly, flotation. And of course, we all know what this is. This is something that's less dense than water, so a specific gravity of less than 1. And opposed to settling out, this is going to float to the top. And a lot of times there's mechanisms on equipment that will skim off the top. Okay. So, and that sedimentation principle, this whole specific gravity principle, density, is really used throughout the treatment train. So like James talked about, it's in preliminary treatment with the grit chambers. It's in primary treatment, so this is when a ton of sedimentation happens, so things really settle out there and get rid of a lot of that TDS and the BOD. The TSS is total suspended solids, and BOD is biochemical oxygen demand. So that's two of the measurements that we're really trying to get rid of when we're going through the wastewater process. It's in secondary treatment. So after the biological process, you have this activated sludge, and you want that to settle out too. So this is a secondary clarifier, and you'll see that the water on top here looks pretty clean, but then down below is that activated sludge that is settling out, and then that's pumped out. So that's through that kind of the typical treatment mechanism for wastewater, but it also can be used, the concept of sedimentation, for other purposes. So this is called a gravity thickener. And this one's actually in a drinking water system, but it's the same concept, and these are used in wastewater. This looks like a regular clarifier, but the difference is that this is pretty deep, significantly deeper, I think, for how small it is. At least it's a pretty skinny tube. And it's actually, I don't know, maybe 75% full of sludge. So this is actually just used as a dewatering device. So the idea is that after sedimentation, the primary sedimentation, the sludge gets pumped into here, and then the weight of the sludge after it keeps getting added, the maybe 15 feet or sludge, it compacts itself as it goes down. And as it compacts itself, it dewaters itself too. So then that water will come out over these weirs, and then the more dense compacted sludge is pumped out at the bottom. Okay, and then sedimentation, it is really all around us. Um, so it's in reservoirs, because of course these streams are flowing into reservoirs and they're carrying sediment, and then they flow into a reservoir and they deposit in the reservoir. So they only have reservoirs have a limited lifespan. It's also in streams. So every time a stream is meandering on the inside of the curve, the water slows down and it creates these gravel bars. So it deposits this gravel on the inside of the curve. And it's also, we use it every day. If you're a coffee drinker, James was talking about tea. Now I'm going to talk about coffee. And so, really, if you make Turkish or cowboy coffee, kind of the idea is that the coffee grounds will settle out. And the reason why I'm sharing this is because, just like James was talking about, with some of that pre-treatment, the sedimentation, flotation. These concepts they're really simple, and so I feel like there's so much engineering and these fancy terms, but it really is the concepts that we know, we think about every day, and having a better understanding about those concepts, just how we see them and what we experience them in our lives. It really helps us troubleshoot things too. Um, so, speaking of coffee, and I know James had a bunch of videos in his section, and I don't have any videos, but I have a live demonstration here. So we're gonna do a little science experiment. So we'll see how this goes. It might not work, but we'll see. Okay, so speaking of coffee, here I have my coffee pot that I made this morning. And so I use these coffee grounds to make a second cup of coffee. And so it's kind of weak right now. You can't really tell on the video, but I have a flashlight. So if you're able to see through, you can see that a lot of the coffee grounds, they have settled down into the bottom of this French press. And up top, you can see that there's this layer that it's not clear because there's still some stuff in there. So that's the stuff that has not settled out yet. And you really can't see it on the video, but there's actually some stuff that's floating on top. It looks like those are maybe some oils because coffee is oily. And so that oil is less dense than water. So it's going to float up to the top. And so, I don't know if we're going to be able to see this at all. Oh yeah, maybe you can. So even if you look at the profile of these coffee grounds that have settled out, you'll see that at the bottom of this French press, there's all these pretty big chunks of coffee grounds. And then as we go up, you can see there's this layer that is even less, that's like smaller particles. And that is there because that took a longer amount of time to settle out. So these bigger particles fell out quick, and so they're at the bottom. And then these smaller and smaller particles take more time to settle out. And then there's stuff that's still suspended, of course. And so this stuff is, these particles can really be called colloids. So you might have heard that term colloids before. And so what that means is these are particles that are so small that the charge of water, so because water is polar, there's a positive side and a negative side to each water particle, the H2O. So that actually, that charge has a bigger impact on these really small particles than gravity does. And so that is why that all these particles that are still there, you can see them, that brown color, they're never going to settle out because of those charges of the water molecules. And so if we wanted to, maybe we could add a coagulant in here and we could chemically help those drop out of solution. I've heard that you can put eggshells in here and that acts as a coagulant. I've never done that, but so there's our demo for today. And so right now you can see kind of what that looks like. So I am going to stir this up. So I'm just going to shake it and we'll see if I spill this. Okay, so now we mixed up our coffee. Okay, and so now if I put my flashlight by this, you're not able to really see it at all. And so I'm gonna let this sit for a little bit, and you can see the big ones have already started to settle out, and some of the other chunks are still swirling around. So, but right now there's still so much in suspension, you can't see my light through it like we could a minute ago. So we'll take a look at that in another little while, and we'll see how it looks. Okay, thanks for
Great demo, Tomer.
Thanks. Yeah, I didn't know how that was going to go. I hadn't really done that yet, actually. So, and that really was my coffee. I just drank some of that earlier. Okay, so can you all see my screen? James, can you let me know?
Yeah, you're back.
Again? Okay, perfect. Okay, and so now we talked about sedimentation, and I did mention flotation a little bit with that coffee kind of going up to the top. So that really happens all the time too in wastewater treatment. I think this is a secondary clarifier, but you can see some oils and some stuff floating up to the top. And so this is actually skimmed off with this little arm that rotates around. And then there's going to be a trough that is going to push it in every once in a while. And this arm is moving very slow because you don't want it to mix things back up. You want to get all that grease and stuff out of there. And then there's also a device that specifically uses flotation to as a treatment method. So this is called the DAF, or dissolved air flotation. Sometimes this can be used just as a thickening, dewatering device. But the idea is that on the left side of this device, there's all these little tiny like air bubbles that are coming up from the bottom, and they work by physically bringing the everything that's suspended in it up to the top of that water column, and then it has all these little like scraper things that are on this chain, and it goes around and it continuously scrapes off those whatever came up to the top into this trough. And then at the same time, it has a pump at the bottom that sucks out the sludge, anything that settles. And then the water that's coming out is from the middle of that water column. So that's going to be the cleanest water that comes out. Okay, and so there's a lot of kind of this theory behind all of this, and we don't need to go into this really too much at all, and you can look back at this if you would like to. But the idea is that there's all these different kinds of sedimentation or gravity separation theory, I guess. So just to go really quick over some of them, discrete particle settling, that means like discrete particles by themselves, so they're not clumping together. So that's going to be like grit, just settling out by itself. Flocculate, of course, that is when particles are bumping together, making bigger particles that settle out. Ballasted flocculate settling, that is when something like sand is added and it kind of acts as like a little like nuclei or whatever. So the suspended solids will attach onto it and settle out. Hindered zone settling. So that is this part that is kind of in the profile that is kind of where it's like where the like kind of the liquid and the solid kind of are in that little boundary. So it kind of acts as like a little blanket and the particles kind of push each other apart. Compression settling, that is what I was talking about with that gravity thickener, is how that the main principle behind that. But of course that happens in clarifiers in general at the bottom. So that is when the sediment itself is pushing itself and squeezing it. Accelerated gravity settling, that's like that that grit removal thing that James was talking about. So if air or something is used to help stuff be removed. And then lastly, flotation. So that's when something goes up to the top, less dense than water. Okay, let's see. Let's launch our first poll. James, can you launch this one if you're able to?
This is number 5, correct? Yes.
Yes. And we'll see. I don't know if we'll have time to go through all these polls. So, but we'll start doing this one. Okay, so all right, so what is flocculation? So this is just single answer. Just choose whatever answer you think is the best. Why would you do that? While you answer it, we're gonna check to see how see-through our coffee is. Oh, and so you can see that there's stuff starting to settle out. So it's definitely not as like see-through. The light doesn't move through as nearly as much as it did when we first started this, because I had let that settle for probably a couple hours. So now you can see that things are starting to settle out at the top, but not as much as we get further down into in the column of coffee. Okay,
All
so
right,
I
let's
think we
give
can
this.
end that poll.
Okie dokie.
Thank you, James. Okay,
See
so it
that?
looks like, yeah, most people said B, that second answer, gathering fine particles together to form larger particles. Exactly. So bigger mass, creating a bigger mass, it falls out of suspension a little quicker. So good job. Oops. Okay. Okay, so now, okay, so we're going to talk a little bit just about the numbers behind grit removal. This is kind of what James talked about, but we're going to add some numbers in here. So if you have a grit channel, so these are designed to remove sediment that is about 0.2 millimeter in size. So that's sand and some grit particles like that. And they typically settle downward at a rate of 0.075 feet per second. So say that we have a channel, I guess it's a basin, we're going to say it's 4 feet deep of water. Okay, so we're going to draw a little diagram here. So we have our settling rate at 0.075 feet per second. So we drew that little down arrow of how quickly things are going down. Okay, and so their settling time is what we want to figure out. So then we're going to have our depth divided by that settling rate that we just had. Okay, so we're going to plug in our numbers. So we have 4 feet of water. So that's that column of water that the sediment needs to settle out of, and that's the settling rate. So if we do that math, it's going to cross out our feet units, and we're going to end up with seconds. Then we're going to end up with 53.3 seconds. So that's really the time that it is going to take for water to settle out in this scenario. And of course, if we kind of visualize this, our flow is moving across the screen. And so if sediment is settling down while it's moving, it's going to take a diagonal path. Okay, and we can figure out um, the length of that path by the velocity of water. Okay, so and we can figure out, so if our water is going out 1 feet per second and it takes 53.3 seconds, and remember that 1 feet per second is what James talked about earlier, it's going to take us 53.3 feet in order to adequately settle out that size of particle. Okay, so of course we have these concrete things and made of metal, so it's not like we can just change the size of our facilities as as things change throughout the day or the season. So of course we're stuck with our channel that say is 50 feet long. So what's the maximum velocity that water can move through in order to get the removal that we want? Okay, so we have our settling time of 53.3 seconds, which we calculated. And then there's our velocity formula there, length over time. And if you're wondering about that formula, we did go over that 2 months ago in our math training webinar. So go check that out if you want to learn some more fun math problems. Okay, so if you plug in our numbers to that, we can figure out the velocity. So our maximum velocity to go through our scenario here is 0.94 feet per second. So that is the maximum velocity of the flow through our channel that in our hypothetical scenario here. Okay, so is this going to be effective? 0.94 feet per second. And if you look at that table, and this came from this Sacramento State guide, if we look at our horizontal velocity to get rid of that grit is going to be between 0.8 and 1.3, which we are right there. So we're doing good. So in theory, we should have adequate grit removal in our scenario. Okay, so, but of course, a lot of times we can't necessarily adjust things that easily, but if you do need to get to that flow, how do you change that? So there's a few things you can do. You can somehow adjust the inflow. Maybe you have an equalization basin at the beginning, like James talked about, and you can adjust the flow. You can change the water depth. Perhaps you have multiple channels that you can open up during higher flow times. Yeah, like ultra flow with the equalization practices. And maybe you have other options. So as an operator, you know your system best. What can you kind of adjust? And also what is practical. Of course, you can't adjust everything. So, but the whole idea behind this and why I went over this math is that there is some math that you can figure out that will give you the best settling of the size of particles that you want. And so if you're not getting very good results from your grit removal system, for example, figure out what you might want to adjust. And then maybe you can improve your removal. Okay, and then also if you need to figure out velocity, you can also steal this stick from this cute little dog and throw it in your grit removal channel or whatever, and you can estimate your velocity. So, but that dog's so cute. I want to steal their stick. Okay, so now we're going to move on from that grit removal and we're going to talk about sedimentation in primary clarifiers. So this is a big part of the treatment process that removes a lot of the TSS and the BOD. And so this is mostly going to remove particles that have a specific gravity of 0.05, specific gravity of 0.05. So that means it's 5% more dense than water. So pretty similar to water. So it's going to settle out relatively slowly. Okay, so if we think about the same kind of process or go through the same process that we did for the grit removal, and I'm going to go through this a little bit quick just for the sake of time. So my apologies. But if you want to review this a little slower, you can go through these slides or watch this recording again later. But so with this, we're going to, of course, have a different settling rate than we will through the grit because this sediment is less dense, so it has a lower specific gravity, a little closer to water. So we're going to assume that we have a settling rate of 0.167 feet per minute, and that translates to 0.0028 feet per second. Okay, and we're going to have a horizontal velocity of 2 feet per minute or 0.03 feet per second in our made-up scenario here. Okay, so of course we're still going to have that same particle path that is going to be diagonal. And then if we want to, we can add our basin length of there. So 200 feet long, and then we have 10 feet of water in our imaginary scenario. Okay, so we're going to write down that formula like we did last time. And then we're going to plug in our numbers in there. So 10 feet divided by that settling rate. And then if we plug that into our calculator, our feet units are going to cancel out and we're going to end up with minutes. So that settling time for particles that size is going to be 60 minutes. Okay, so if we go from there with our 60 minutes, so what's the horizontal distance that those particles are going to travel before they adequately settle out? So we have that horizontal velocity of 2 feet per minute. And then we're going to use our velocity equation there again. So, and we're going to rearrange it. So we have our unknown, that length on one side by itself of one side of the equal sign. And we're going to plug in our numbers and cross out our units. And so we're going to end up with 120 feet. So in our example, we had a basin that's 200 feet. And so in theory, all of these particles that are that specific size and density are going to fall out within that first 60% of this chamber. But of course, this is all in theory. Of course, there's going to be different rates that different particles settle out. So of course, you're going to have settling throughout this whole basin. But calculating this out is really great to know because it can help you with processes and improving your treatment if that needs to happen. Okay, so what's kind of our expected removal of total suspended solids and biochemical oxygen demand. So we can actually figure this out, figure out how much of this is removed through our treatment. And so some smart people came up with this equation. And so it's the removal efficiency on one side, and then on the other side, we have our variables, our nominal detention time, and then we have these constants. So these constants are in this table right here. And I don't know how they figured these out, some smart engineer or somebody. But if we use the values that we calculated earlier, we can plug it into this equation, and then we can figure out what is our expected removal of total suspended solids and biochemical oxygen demand. So in this scenario, we can plug in those numbers, and we end up with our expectation of 56.3 removal of total suspended solids. And then for BOD, we're going to expect 35.5% removal. So that's what we expect, but you can also calculate these by what's actually happening in your facility. So this is a slide that I took directly from our wastewater math video that I did 2 months ago. So I went over this more in depth, and you check out that video if you want to see how we went over these. But the idea here is that you can figure out what is expected for your removal of TSS or BOD, and then you can actually compare it to what's happening. You can use this equation to figure out what is the TSS coming in, what is the TSS going out, and what is that actual percent removal. So, and then you can use that to maybe adjust some of your processes. Okay, so briefly, I'm going to talk about detention time. So this is important, of course, because particles take a while to settle out. And so depending on how long they're in any given vessel, different sizes of particles are going to have time to settle out. So typically, these settling tanks are designed for 2 to 3 hour detention times, although, of course, different systems might vary. And with your experience can come into play when you can decrease or increase flows suddenly, or when the flows do increase or decrease, maybe you need to adjust some different processes to help the settling. And then, like I talked about, you can calculate the theoretical detention time with your specific scenarios and compare different times. Like what happens with your flow when it's during your peak flow hours versus at nighttime or something. So you can figure that all out. And then the actual detention times are smaller than what you calculate based on your tank. And if you want to do detention time calculations, go watch that wastewater math video. But a lot of times you need to include a baffling factor. So a baffling factor just means that what is the water moving through all equally through a chamber, or is it short circuiting? Is it going through quicker one area and slower another area? So of course these basins are not designed perfectly, or it's not possible to design it perfectly where everything flows through exactly equal rate. Okay, how are we doing on time? Let's see. I'm gonna skip this one. We're just gonna keep going for a second, but let's check out our coffee. Okay, so I think we're settling out quite a bit more than last time we looked, even from the last poll question. So now with more and more time, we're getting more and more of that sludge on the bottom. So kind of cool to see it settling out more in real time. Okay. Okay, so in the diagram like the math that we did earlier, we didn't include where the water is really coming out. And so it's not just going out the end, it's going out through weirs. And so these are represented by these little orange rectangles up here. And so here's what they look like in real life. These are weirs in a clarifier, in a circular clarifier. And so just so you know what we're looking at here. The water is coming out from the center of this clarifier, or it's coming from that center. It's flowing out in this basin, and then it's actually going underneath this baffle, and that baffle is used to collect anything that's floating, and then goes up and through these weirs. So these weirs are designed to have a specific amount of flow through them. And so that flow is called the weir loading rate. And so this is another calculation that you can do to figure out, to see what your plant specific conditions are versus what is kind of ideal for removing the TSS or whatever you're trying to remove in this, or what you're having problems removing or whatever that may be. Okay, so for that weir loading rate, so this is just the number of linear feet on the clarifier in relation to that flow. So it's 1 linear foot per day is what what that kind of measurement is. And so what the typical design parameters are is 10,000 to 20,000 gallon per day per foot of weir. And of course, it's possible that your situation might be a little bit different, but 10,000 to 20,000 GPD is pretty typical. And then the secondary clarifiers and high quality water will require like lower weir loading rates than what is acceptable for a primary clarifier, and that's just due to the different how much stuff is in the water to start out and end with. Okay, so how do we calculate this? Okay, so there's a formula for this. So here's our weir loading rate, and it's Q divided by L. So it's a pretty simple equation. Our Q is flow rate per day, and our L is the length of that weir. And so note for a circular basin, to figure out the length of that weir, you're gonna have to find the diameter of the weir going around to figure out that length. So whereas in a rectangular basin, you could just measure it. Okay, so in this example, there's actually 2 weirs. So there's one on the inside and then one on the outside. So we need to take both of those into account. Okay, so in this example, we're going to have the diameter of that first weir, or I guess this is going to be the outside weir, of 75 feet, and then of the inside one as 70 feet. And then our Q, so our flow, is going to be 5 million gallons per day. Okay, so first we need to figure out the length, and we're going to use these weirs, the diameter, to figure that out. And then if you add those together, multiply by pi, we're going to end up with 455 feet of weir. And so then if we plug that into our equation, it comes up to 5 million gallons per day divided by 455. And then, okay, and then we end up with about 11,000 gallons per day per foot. Yeah, and that is a goldfish in the tank. And maybe at the end, James can talk more about that, because James is the one who took that picture. So I think it's pretty neat. It's a very creative way of wastewater treatment. Okay, and so in our example here, we end up with 11,000 gallons per day per foot. So we are well within that typical design parameters between 10,000 and 20,000. So that's great. Okay, and just really quickly, I'm not going to go over this, but there's a few other calculations you can do, and these can help you with troubleshooting. So this is the surface loading rate. So as opposed to the weir loading rate, this is actually related to the surface area of your clarifier. So this is gallons per day per square foot of clarifier surface area. And so sometimes this can be helpful to calculate, pretty big range there. But sometimes this is important depending on a colder region or warmer region, because you want to make sure your flow is adequate and it's actually not too low of a surface loading rate to result in a septic condition. Things are in there for too long. Okay, and then just another equation that I'm not going to go over, but just want to mention in case it's helpful for your troubleshooting. There's also what's called the scour velocity. And so this is a bit more complicated of an equation, a bit more intense math with some variables and stuff in here. But this really is to figure out what the conditions are for scouring. So that means for the velocity of that water to flow through something, and instead of depositing sediment, what's the velocity where it's actually going to start picking things up and taking it with it. So that's, of course, not what we want when we're trying to have things settle out. But we want to have a scouring velocity in our collection system, of course, because we don't want sediment to fall out in our collection system. We want it to all settle out in our treatment process. So we want to make sure that our water is not moving too fast in our treatment process to have scouring. Okay, and just like I was talking about, you can use these equations to figure out what your specific situation is in your plant. Maybe you're outside these design parameters, so you can adjust things and then compare them with your actual lab tests, those bench tests, to do some process control. See what your results are versus what your expected treatment is, or your removal percentage. Okay. Okay, I'm actually going to skip this one too, and then we'll do one more poll at the end. Okay, so there's a few things that impact sedimentation, and these are just a few examples that we're going to go over. Okay, so temperature. So this especially is important for places in the northern US, or really anywhere that has much of a temperature swing, so probably everybody here. So water, so even when we're thinking about specific gravity of water, we kind of think of water, the density, as a constant, but it's actually not. The density of water changes with temperature. So in this graphic that I think James made earlier, but we have all these little blue dots here, and these represent water molecules, and where the big black dots are the particles. And so you see in warm water, all these little water molecules are further apart because there's they're hotter, there's more energy in them. So all the molecules, all the atoms in them are doing a lot more of doing a little dance. And so they're pushing away each other a lot more than colder water. So in this colder water, there's less energy. So all these water molecules, the atoms in them, are not moving as much. They're shivering. They're just all huddled together. And so they're closer together, and that actually makes the water more dense. So with sediment settling out, it's going to settle out a lot quicker when these water molecules are farther apart. The water is going to be less viscous than it is when it's going to be closer together. So just think of that as like trying to move through honey versus like some nice water. Okay, and then short circuiting, I mentioned this earlier, but short circuiting can have a pretty big impact on sedimentation. So in this example, we see the water flowing in on the left and then it leaving on the right. And so you can see that it's kind of going up in this arc. So we have this high velocity area, and then we have a low velocity area. And so this, of course, means that the water, or the sediment, might settle out more in this low velocity area than this high velocity area. And it could mean that in this low velocity area, maybe the sediment and the particles there will start becoming septic and start causing odor issues or something. So really it's beneficial to reduce the amount of short circuiting however you can. And so this can happen in a few different scenarios, and temperature can actually have an impact on this. So in this example, we have a colder basin and warmer water coming in. So because colder water is more dense, we have our warm water coming in at the top, and it just flows across the top and then just exits. It doesn't mix in the whole basin. And we have a high velocity area and a low velocity area. And the same thing can happen if it's the opposite. If we have cold water coming in, it can just go down to the bottom, have a high velocity area at the bottom, and then exit out, and we have that low velocity up at the top. So to prevent this, one way to do it is baffling. So this is kind of an extreme example, but the whole idea is that the water takes a serpentine path through the chamber. So really the water is moving at a pretty constant velocity throughout the whole process. And you'll see this a lot in drinking water because you have to have that CT for disinfection. But it's the same concept. Also, you can have plate settlers. So this is kind of, instead of having a weir, these are a bunch of stainless steel plates that are put in an angle, and the water has to go down below them and then up along these plates, and they kind of are slippery, and so things kind of settle out and slide down these plates, all the sediment, and then it goes up and then it pours out into these troughs. So these can kind of artificially increase like the surface area of your basin. And then also microbes. So the composition of what microbes are in that water, they may like to stick together more, or they may like to push apart more. And this, I guess the variable more so maybe is in the secondary clarification with that when it has to do with sludge age. But just know that particles or microbes are interacting with themselves, with other bacteria and particles throughout the whole process. So it can help with that flocculation. Okay, let's do one poll question. Yeah, I know we only have a few more minutes, but we're getting close to the end. So James, you can launch that last poll.
So this is 8. All righty.
Yes.
Here we go.
Okay, so what factor can affect sedimentation? And choose all that apply. End our poll and share the results. Okay, great. So yeah, exactly. So these can all have an effect on sedimentation. So none of these were technically in the last few slides that we went over, but air temperature, of course, is going to have an impact on the water temperature coming in. The flow rate, we did talk about that a ton earlier. That's, of course, going to have a difference. Flock size, the bigger the flock, the more mass is going to settle out. And then, of course, operator attitude, that was just a silly one at the end. But really, if you have the right attitude, you can do all this troubleshooting, you can do some of these calculations, you can do some tests, and you can figure out how to improve your removal sedimentation process. So great job. Okay, so we're pretty much at the end here, but I just really quick. The last step where there's a lot of sedimentation, of course, is in secondary treatment. So this is really after the activated sludge, that biological process. And that's where a lot of the nitrogen and phosphorus and those processes, the removal of those is going to occur. But then you have that activated sludge that then goes into secondary clarification and then is removed from this secondary clarifier from the bottom, is pumped out. And there is a blanket of sludge in there too. So it looks pretty clear here, but then there's pretty big separation between that sludge and the clarity of that water. Okay, so that's all the content we have. We'll continue on in this process and talk about the activated sludge process. And that one, I guess, is going to be in 2 months. But next month, we're going to talk about treatment ponds. I'm going to go over that, and then AJ is going to go over the fixed film media. So come back for that one. And then we can answer any questions. And here is our contact information. And let's feel free to unmute and raise some questions. And I'm going to take a look at this coffee, see how we're doing. Okay, so I feel like every time we look, there's a little bit more light that goes through because more and more is settling out. So now there's not, our coffee is going to be very weak.
It's a great demonstration.
Thank you. And I'm not done yet. So now I'm going to have, I brought my mug, and so now I'm going to have a cup of very weak coffee. So that's also very cold because it's been sitting here for 2 hours.
Still got a kick though.
I'm sure it'll get me going, I'm sure.
Yeah, the caffeine's not going to settle out.
Exactly. Yeah, exactly.